Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the law of large numbers. Our goal is to analyze the properties of the sample mean and to show under what conditions it converges when we take the sample mean over a large number of measurements. The prerequisites are independence and expectation. Let us begin with a motivating example. Imagine that we want to estimate the average height in New York City. What do we mean by average height? Well, if these are the heights of every person in New York City, where big N denotes the total number of people, about 8 million, then the average height is just adding up all the possible heights and dividing by the number of people. We want to estimate that number. Of course, we could go ahead and measure everyone in New York City, and we would get a very good answer, but this is not going to be practical. And this happens in many problems, where you cannot just go and measure each individual in a very large population. Instead, we're going to take another strategy, which is very popular in practice, which is random sampling. The idea is that we're going to select a subset of n individuals, and we're going to base our estimate of the average height on those individuals. We're selecting the individuals at random and with replacement, which means that potentially we could pick the same individual twice. That's not really important. It's actually going to happen with very low probability for if we're doing this, for example, in New York City and there's 8 million people. Anyway, so our height measurements, we're going to represent them by x1, x2 to xn, where this is little n, which is much smaller than the big N of the number of people in the whole population. Notice that these are random variables because we're picking this subset at random. What is the probability that each of the random variables is equal to one of the heights in the population? Well, if we pick this subset uniformly from the population, so that means that every individual has the same probability of being picked, the probability that each of these random variables equals one of the possible heights in the population is just 1 over big N, where big N is the number of people in New York City in this case. Okay, so let's think a little bit about the properties of these random variables. If we pick with replacement and independently, which means that we don't care whom we have picked before, we just pick another. So you would pick a person out of the 8 million, we leave that person there again, and then we pick again. So potentially we could pick the same person, probably we'll pick someone else. In any case, the choice is independent. In that case, these random variables are independent, right? They're also identically distributed because we're doing the same thing at each time we pick, right? We're picking from the whole population uniformly. Those random variables have the same distribution, so they are identically distributed. Let's think about what is the mean of these random variables. The mean, by definition, is, in this case, these are discrete random variables, right? Because they take values only in the possible values of height in the population. So we have to sum up over all the possible values, which are the heights in the population, and we have to weight them by their probability. This is the definition of the expected value of this random variable. We take all the possible values, we weight them by their corresponding probabilities. We have already seen that this probabilities is just 1 over the number of people in the population. Those are the heights. So we see that the expected value of each of our measurements is exactly the mean of the population that we are interested in. Okay, and this seems like a good sign. A reasonable estimator for this population mean is just taking all our measurements and averaging them. Okay, so the idea is quite simple. We can't average the whole population. How about we just take a random subset out of the population and then we average them? Is this going to work out? Well, we will see that according to the law of large numbers, it will work out. Here is just a sneak preview. What I've done here is I've taken a subset of 100 people out of a population of 4,000. So here I'm using a real data set of heights from people in the US Army. I selected 100 of those 4,000 people, and I did this many times. I did this 10,000 times. And then here we can look at the histogram of the sample means corresponding to those n measurements. And what we see is that it's actually pretty close to the true population mean, although there is some variation. Okay, and the law of large numbers is going to tell us under what conditions can we expect that this distribution will concentrate around the true mean, which is in this case 175.6, as n, and by n I mean little n here, the number of people that we select, as that becomes larger and larger. Let's look at another motivating example. In this case, we want to estimate the proportion of people in New York that have COVID-19. So here we have defined a deterministic variable for each person that tell us whether they have COVID-19 or not. If they don't, this would be the variable is equal to 0. Big M people have COVID-19. Our goal is to estimate the proportion of infected people, which we called theta of the population, which is equal to it's equal to the sum of all of these variables, because these are equal to 1 if the ith person has COVID-19. This proportion is just going to be equal to m over n. This is what we want to estimate from the population. What could we do? We could go ahead and test everyone. But of course, that would not be feasible, either financially or practically. So instead, what can we do? Well, we can do the same thing as before. We can select a subset of n people from the population and perform random sampling. Again, we're going to pick n individuals independently at random, uniformly from the population, with replacement. That means that we could test someone twice, potentially, or more times. Okay, if we denote the test results by x1, x2 to x little n, these are again random variables. The randomness, by the way, is injected by ourselves when we are performing this selection, right? In the original population, there's no randomness. We are introducing the randomness into this problem due to our limitation where we cannot test everyone. We say, okay, we're going to test a subset, and we have decided to pick that subset at random, which is a very powerful idea. Okay, so what is the probability that a person that we pick at random actually has COVID-19? This is the probability that, this probability is the probability of the union of the events that we have picked someone with COVID-19, right? It's the union over all the AIs in the population that are equal to 1, all the people that have COVID-19. What's the probability that we have picked one of them? These are disjoint events, right? Because we either pick someone or we pick someone else. So we can sum these probabilities. And now this sum is equal to, this probability is just equal to 1 over n, because we're picking everyone uniformly at random, right? And this sum is over the people that have COVID-19, and we know that that's equal to big M. So the probability that we pick someone with COVID-19 is exactly equal to the proportion that we want to estimate. So each of these guys is a Bernoulli random variable, and its parameter is equal to our proportion of interest. What is the mean of that Bernoulli random variable? It's its parameter, right? Because remember that for Bernoulli random variables, the mean is just 1 times the parameter plus 0 times 1 minus the parameter, so just equals the probability that it's equal to 1. Okay, so again, we have a situation where we have generated these IID random variables, and we want to estimate their mean. Okay, their mean happens to be our parameter of interest, and a reasonable way to estimate this mean is to use the sample mean, just like before with the heights. Okay, so these random variables are independent, they're identically distributed, and a reasonable estimator for our parameter of interest, which is the proportion, is again the sample mean. Because our parameter of interest is the mean of each of these individual random variables. Another sneak preview, let's imagine that the prevalence of COVID-19 in New York City is 0.05. Now, thankfully, it's a bit lower, but when I designed this example, it was still around 5%. The total population is 8 million, and here what I've done is I'm showing the distribution of 10,000 sample means where we have selected 100 people. And as we see, sometimes it deviates a little bit, but in general, it's around the value that we want to estimate. Again, the law of large numbers will tell us that if n is large enough, eventually we're going to get a good estimate of the proportion. But let's not get ahead of ourselves. Let's take a look at the properties of the sample mean. We want to understand when the sample mean will tend towards the true mean of the IID random variables as the number n increases. The first step is to see where this distribution is centered. What is the mean of the sample mean? You might be a little bit confused here, but remember that these guys are random variables. We're picking the people at random with replacement. So if we take the sum of these n random variables and divide by n, that's still a random variable. The sample mean is random because it depends on the choice that we have made when we have selected the n people. Okay, so please remember here the sample mean is a random variable. And what is the mean of this random variable? Well, by linearity of expectation, this is quite easy. The 1 over n comes out, the sum comes out. We just have 1 over n times this sum of the mean of each individual random variable. And we are assuming that they have the same mean, which is the parameter of interest in our two examples, in our two motivating examples. So this tells us that the sample mean is centered at the right place. If we have some random variables with a certain mean mu, their sample mean is going to be centered at mu. It's going to be equal to the expected value of their sample mean is going to be mu. Notice that here we are not making any independence assumptions. This will hold because of linearity of expectation no matter what dependence there is between these random variables, as long as each of them have the same mean. Okay? As we will see, this is not true about other important properties, in particular the variance. Okay, so this means that the sample mean is an unbiased estimator of the true mean. In statistics, the average error that you make when you estimate something is called the bias. This says that, on average, our estimate is actually perfect, but only on average. It can have a lot of fluctuations. So just to go back maybe to our picture, this just says that the distribution of the sample mean is centered at the right place. It doesn't say, how spread out it is. So maybe sometimes we make a huge error in this direction and then a huge error in that direction and they cancel out. That would be a terrible estimator, but it still would be unbiased. It still would be centered at the right place. So we need more. Okay, I should have asked you to think about this, whether this was enough. This probably would have been more instructive, but sorry for spoiling. Let's take a look at the variance. Let's take a look at, on average, how much this estimator fluctuates. In order to understand the variance of the sample mean, we have to look at the variance of a sum of two random variables. And in particular, we're going to be interested in independent random variables. Okay, so what's the sum of the variance of two independent random variables? We're going to use the definition of variance where we write the random variable of interest, which is a plus b, minus its mean. And now what we're going to do is we're going to split this. We're going to split this into a minus its mean. I'm going to write the mean like that because it's just easier. Plus b minus its mean. And we're going to expand out the square. Okay? And then by linearity of expectation, we're going to separate the different sums. So we've done a minus its mean squared plus b minus its mean squared plus twice the cross terms between a minus its mean times b minus its mean. But now we realize that this and this are independent random variables. Okay, so what is the mean of the product of two independent random variables? It's the product of their means. Okay, we already went over that. So we end up with the expected value of A minus its mean squared, which is just the variance of A, plus the expected value of B minus its mean squared, which is just the variance of B, plus this cross term, which can be written as the expected value of A minus its mean, times B times times the expected value of B minus its mean. However, here, by linearity of expectation, we have that this is the expected value of A minus the expected value of this thing, which is just a constant. So it can just come out, and this is actually the expected value of A minus the expected value of A, so this is 0. So this means that this cross term cancels out, and the variance of the sum of two independent random variables is equal to the sum of their variances, which will not happen if they're not independent, because in that case, this term will not separate into the product of the two individual expectations, so it will not cancel out. Okay, so now, of course, before on purpose, I didn't include that these guys were independent, and then I forgot to add it back here. So it's absolutely crucial that these guys are independent, okay? So what happens if we take the variance of the sample mean of n independent random variables? Because they're all independent, first what we're going to do is we're going to take this guy out before considering the sum. Remember that when we multiply a random variable by a constant and we take its variance, the variance is multiplied by the square of the constant. Okay, because the variance is just the expectation of a squared quantity. So first we take this guy out with a square, the 1 over n, and now we have the variance of a sum of independent random variables. This is just equal to the sum of their variances, and each of these guys is just equal to sigma squared. We are adding the same number n times, so it's equal to n times sigma squared. We end up with a variance that is sigma squared over n. Okay, and again, these guys have to be independent. Otherwise, this does not work. This is awesome because it means that, so okay, let's think about what we're talking about. This is the spread of the sample mean around its mean, but we saw that the mean is exactly the population mean that we want to estimate. So if the spread is becoming smaller and smaller and smaller with n, this is exactly what we want, right? This tells us that as n grows large, our estimate is going to be more and more concentrated around the truth. And that's actually the law of large numbers. We're going to dwell a little bit on the details, but that's essentially it. Because the variance goes to 0, that means that eventually the estimate becomes perfect. End of story. Again, we're going to provide a lot more details about it, but that's the key. Okay, so again, I forgot to put here that these random variables are independent, but maybe this is good because hopefully it will, the importance of independence will be imprinted upon you, because I'm going to have to repeat it over and over. Here we're looking at the mean squared error between the sample mean, which is this estimator that we obtain, for example, when we're doing random sampling. We take these n people, we take their average height, or we take these n people and we see how many of them have COVID-19. That's our estimator, and this is the parameter mu that we want to estimate, okay, which corresponds to the mean of each of these random variables. Okay, so what is the mean squared error of this estimator? Well, this is just equal to the sample mean minus its own mean, right? Because we've seen that the mean of the sample mean is just equal to mu. Now, this by definition, what is it? It's just the variance of the sample mean. Okay, so the mean squared error is actually equal to the variance, and we have just seen that the variance is equal to sigma squared over n. So in particular, if we take n to infinity, then this whole thing goes to 0. Okay, the mean squared error tends to 0 as n goes to infinity. And now I'm going to write here that these random values have to be independent, because otherwise this won't work out. This part still works out, right? Because we've seen that their mean, they're always centered at their mean as long as they all have the same mean, but this would definitely not work out if they're not independent, because this cross term in the variance would not cancel out. So we see that the mean squared error of the sample mean goes to 0 as n goes to infinity, and this is the law of large numbers. Let's go back to our two examples. First, the height. We were selecting n people at random. Each of them was equal to, well, the height of each of them is equal to one of the heights in the population, 1 over n. The mean of each of these random variables is the mean of the population, which is what we want to estimate. The mean of the sample mean is the mean of the population, which is what we want to estimate. And now we need the variance, right? Because here in our result, we have seen that this depends on the variance. The variance needs to be finite. So we have to check that the variance of this height is actually finite. So what is the variance equal to? Let's compute it, the population variance. It's equal to the expected value of these random variables minus their mean. We've seen already that their mean is the population mean. So essentially what do we need to do? We need to see all the possible values of this random variable, the square of the heights of the people we select minus the population mean, squared. And all the possible values are just AI minus the population mean, where these are the possible heights of the population of the people in New York or in whatever population we're interested in, summed over the whole of the population. And of course we have to multiply, because we're taking this expected value, by the probability that xj is equal to that particular height value. But we've seen that this is just equal to 1 over n. Okay, I feel that I annotated this a lot. This is just equal to 1 over n. So essentially what we get is the variance of the whole population, meaning the average of each height minus the mean height in the whole population, squared and then divided by the total of number of people, either in New York or in the population of interest. We're going to call this parameter sigma squared population. This is the population variance. In our data set, it's equal to it's equal to the square of 6.85 centimeters. Remember that when we're dealing with variances, we often take a square root to convert them to standard deviations so that they're in the same units of interest. So in our data set that we're using for our numerical experiments, which is this height data from the US Army, the true mean is 175.6 centimeters, and the true population variance is 6.85 centimeters. Obviously finite. And notice, by the way, that the population variance is always going to be finite as long as you have a finite data set. We'll talk more about this in a subsequent video. Anyways, we have a total population of 4,000 people. What happens if we just take 20? Well, our estimate is centered, as it should be, and it has a certain variance, which is essentially equal to the square of this divided by 20, by what we just saw. So as we increase the number of people, now we take 100 people, it starts concentrating. If we take 1,000 people, it concentrates very tightly around the true value. Okay, and this is what the law of large numbers predicts. Here, I'm showing you a scatter plot where I'm changing n, I'm modifying n from 0 to 1,000. So we've seen slices of this, right? We saw like 20 people, so basically a slice here, a slice at 100, roughly there, and then a slice at 1,000. And just to make sure we explain what this means, each of these points is a sample mean taken for the population with a number, like a sample mean over n people. Okay, and what we see is that at first the sample means are quite spread out, but little by little they become less spread out. And this is what the law of large numbers tells us. Eventually we converge to the true population mean. Here I've stopped at 1,000. If you continued, it would just collapse eventually. Okay, so random sampling works is our conclusion. Now we're going to look at our other example where there were these people that had COVID-19. We want to find out what the proportion of people with COVID-19 in the population is. We have this n subset of people. We have selected them independently and identically at random, uniformly from the population. The probability of testing someone that has COVID-19 is exactly the proportion that we're interested in. This is a Bernoulli random variable. Its mean is equal to its parameter. Its variance is just equal to the parameter times 1 minus the parameter. Okay, we already derived this. It's actually easy to derive. Just think of the mean square of the Bernoulli and you subtract the square of the mean. So this is good because it has a finite mean. So things should work out. And indeed they do. Okay, so this is what we get when we pick 100 people. When we pick 1,000, it starts to concentrate. Again, always centered around the true proportion that we want to estimate. And when we pick 1,000, it concentrates really, really a lot. Okay, so we get a very precise estimate. No matter which of these sample means we choose, we get a very precise estimate for the proportion of people with COVID-19 in the population. This is the same plot as before. Notice that it's a little bit weird here, but that's just because we're adding up Bernoulli random variables. So when we don't have a lot of them, they have like these possible discrete values. Okay, here we're just adding like between 10 and 100. But anyways, the same thing happens. This is the true mean. Oh, I forgot to say in the previous plot that these lines here, actually let me go to the previous plot and just make sure. The previous plot about the heights. Okay, I just want to make sure that I explain these two lines here are exactly equal to the true mean plus and minus the standard deviation over square root of n, which is the deviation that we expect for each of the n's according to our computations of the variance. And we see that indeed the distribution concentrates in exactly that way. Okay, I should have made more of an emphasis on this. Sorry about that, but at least I remembered. So now let's go back to our case where we were estimating the proportion. And here, same thing. Here, this is, sorry, maybe let me erase this and let's start from the beginning. Here we have the true proportion that we want to estimate. For every n, I'm putting here a scatter plot of points of sample means, and we see that they concentrate. So before I showed you for 100, for 1,000, and for 10,000. Okay, those are the distributions that I actually showed you in detail. And as we saw, they concentrate very tightly. And the way they concentrate follows these two curves here around the true proportion in the population, and those are just the proportion plus minus the standard deviation of the sample mean. Okay, just to show you a connection with the proof of the law of large numbers. The proof predicts that that's what's going to govern the deviation of the sample mean from the true mean that we're trying to predict, and we see that this holds numerically. What have we learned? The sample mean of IID random variables with finite mean and variance converge to their mean in mean square. And as a result, random sampling works very well. Thank you very much.